Next, let's talk about some properties of interior closure in local base. First, let's start with a little observation. If a point P lies inside the closure of a subset of X, then for every neighborhood of 0, of course, the intersection, well, I should write as V. So P plus V intersects the set should be non-empty. And it's very easy to see that. So that V be any neighborhood of 0 as above, and E be any closed set that contains A. Then we have the following equivalent properties. So first, if it is in the closure, by definition, it is in every closed set contains A, right? Next, it will not be contained in the complement of it. And if we add a neighborhood to this point, this set minus the complement of the closed set should not be empty. If it is empty, it means that it lies inside E, and it will be outside E. That will be a contradiction. And next, it is equivalent as saying their intersection is not empty. So it's true for every closed set that contains A and every neighborhood. So this is true. So let's start the theorem. Theorem 1.13, which is regarding the properties of closure interior. So let's prove the statements that we stated. So the first one, it says that if A is a subset of a space where X is just a topological vector space, then the closure is the same as neighborhood, the intersection of this collection, where V is every neighborhood of 0. And the proof simply following from the observation above. So if P is inside A, as we proved above by star, for every neighborhood, we have that their intersection is non-empty. And by the proposition we proved before, we can move the V to the other side. So this becomes this. Since V is a neighborhood, if and only if the minus V is a neighborhood, so we can also just turn the minus sign to a plus sign. And this is similar as saying that the closure of A is the intersection of all these sets. So that was easy. Second one, it says that A and B are two subsets of X. Then the closure of A plus the closure of B contains in the closure of A plus B. And this again follows by the property we had before, the star. So we want to prove that the point that's called A in the closure of A and B in the closure of B, and want to prove that A plus B lies inside closure of A plus B, which is equivalent as proving for every neighborhood of 0 we have, that's called a neighborhood of A plus B. This is non-empty. So first, we start with the neighborhood W, which is the neighborhood of A plus B. Neighborhood of A plus B. And by the continuity of addition, there exists W1, W2, which are neighborhoods of A and B, such that the sum of these two neighborhoods is contained in W. So this is the definition of continuity. And because they lies inside the closure of A and B, so again by star, since A lies in this set, there exists X lies in W1 intersects A. And similarly, we have Y inside W2 intersects B. Then we just add these 2 points together. We will get that W1 plus W2 intersects A plus B contains a point X plus Y, which is contained in W intersect A plus B, which is what we're trying to prove over here. Okay. Next. So if Y is a subspace of X, so that's closure of Y. And that's very easy. So by the definition or the condition that we need to check, first 0 needs to be in this, right? But because Y contains, the closure of Y contains Y, so this is obviously true. Next, for every two scalars, the following condition needs to hold. Containing this. So first step, we can just write it as this. This step is due to the fact that the scalar multiplication is continuous. And by B, this is by B. This is containing this. And because Y itself is a subspace, so we have this. So this is done. So this is by Y is subspace. So again, C is done. Okay, next, D. D says that if a set, a subset of X is convex, then so are its interior enclosure. So recall the convexity. This means that for a scalar lies between 0 and 1, this equation has to be true. So for the closure, it's very easy. It's again by B. And the fact that the scalar multiplication is homeomorphism. So first step, we just can move the closure to the whole thing. The next step is by the fact that C is convex. So the closure part is very easy. So the interior part. So because interior is contained in the set itself, we have the following property. So first, we just write this, which is contained in without interior. And by definition, it is convex, so it's also contained in C. But the set at the very left here is an open set. So by definition of interior of C, it contains this. So that proves it. Next, part E. So if a set B is balanced, so R, not so R, we have a extra condition. So if B is balanced, first it contains, the closure of it is also balanced. Furthermore, if it contains 0, the interior contains 0, then so does the interior. So for the closure part, it's again very easy. So just let alpha be a scalar that has absolute value that's equivalent 1. Then we want to prove that this is contained in B, right? But by the fact that scalar multiplication is a homeomorphism, we have this, right? And it just follows by the fact that B itself is balanced. By the way, if alpha is 0, there has nothing to prove, so we just skip the exception, because alpha will not be a homeomorphism if it is 0, but we don't need to worry about that. So the interior part, so as we can see, if B is a arbitrary balanced set, it is possible for it to not contain 0. You just take an easy example, something like that. Then if you take the interior of this set, it will not contain an origin, so you have to assume it. So 0 is in the interior of this set. And same as before, for alpha that is smaller than equal to 1, since this is a homeomorphism, this will be the same as this. Then this will be contained in B. So that's it. So the special part about this is that, so we have to exclude 0 here, and let's put 0 right down here. If alpha is 0, because 0 lies inside the interior, so alpha times it is actually the 0 set, which is contained in the interior. So that's also fine. So you have to be a little bit careful about the interior, because it is possible that it will not contain the origin. So next, we have that if E is bounded, then its closure is also bounded. Notice that the interior is obviously bounded because it is inside the set itself, right? So we can take the same constant that we need. So that's that VB a neighborhood of 0. So we need to prove that there exists some constant S positive, such that E lies inside TV for T larger than S. This is what we're trying to prove, and it's a definition. Oh, forgot to take a closure. So to prove this, we use the property that every neighborhood contains a neighborhood, such that the closure is contained in the neighborhood. So this is a theorem that proved before. This is theorem 1.11. So we proved this before. Then now we use this neighborhood W to apply the boundedness definition. So by definition of boundedness, and we apply this to E with respect to the neighborhood W. So there exists a positive number S such that E is contained in TW for T larger than S. And we just take closure of both of these sets. Now, the very last step just follows from the fact that the closure of W is contained in V. So we prove it. Okay, let's finish the property of interior enclosure. Next, we want to discuss that every neighborhood contains a balanced neighborhood. So theorem 1.14. There's two parts. So every neighborhood of 0, of course, contains a balanced neighborhood. And furthermore, if this neighborhood is actually convex neighborhood contains a convex balanced neighborhood. So the construction is actually very easy. It's a little bit tricky to verify the condition though. So let's start with the first one, which is the easier part. So just let V be a neighborhood of 0. And we want to find a neighborhood such that it is balanced and it is contained in V. So the way we do that is use the continuity by continuity of the scalar multiplication at 0. So by definition, there exists a neighborhood and a positive constant such that for any scalar minus 0 that is smaller than delta, alpha W will lies inside this neighborhood V. So what we do is we just take the, let's see what would be a better notation. Okay, let's make this U here and make this V. Make this U here and make this V. Okay, this should be consistent. So we define the set W to be the union that runs all the scalar that is smaller than delta. Then this is obviously balanced, and it is obviously containing U because it is true for every alpha. So the first part is very easy. It is done. The second part though is a bit tricky. So as before, we let U be the neighborhood that we're working on, and it's convex now. So it's a convex neighborhood of 0. And this time, we define a set A be the intersection for every scalar of absolute value 1. And we intersect alpha u together. So our goal is to prove that the interior of A is our desired set, that is convex, is balanced, and is contained in U. So first step, as we said before, it does not necessarily contain 0, so we need to prove that first. So, okay. So by A, there exists W such that W is balanced and it contains in U, right? And we use the fact that since W is balanced, so for every alpha that has absolute value 1, we have the fact that alpha inverse times W is still the W itself. It's fixed by alpha because it is balanced. Then we just move this to the right hand side, right? Because combine these two equations together, we have the fact that it is contained in alpha u. Because this is true for any alpha with absolute value 1, we see that W is actually inside the set A. Then because W is a neighborhood of 0, hence the interior of A is also a neighborhood of 0. So this is the first step. It contains 0. And second, the convexity. The convexity is very easy because every alpha u is convex. So the intersection of all these sets is still convex. And this is A. And by the previous theorem, its interior is also convex. So finally, we want to prove that it is balanced. So balanced. What we do is, for any scalar, so for any scalar smaller or equal to 1, we can write it as r times beta. So this is the scalar, where r is a positive number between 0 and 1, and beta has absolute value 1. You can think it as a phase of a scalar. And we observe that r beta A, by definition of A, it is equal to the intersection of r beta alpha A, because both beta and alpha has absolute value 1, so you can absorb beta by alpha here. So we can write as. Then since, I make a mistake here, it should be u. So these are u. Since u is convex, that contains 0, by the way, it's proven in 1. So we have the fact that for this scalar r, let's do it first, okay? So for the scalar r, we have the following equation. Ru plus 1 minus r times 0 is contained in U. And because alpha is a scalar modification is a homeomorphism, so we can just multiply it by a scalar, which is non-zero. So the final step here is that we can actually absorb R at the very last step, equals, and it's contained in alpha U, which is A again, because R beta is arbitrary constant that is smaller than 1. We prove that as a interior, A itself is actually balanced. So A is balanced. Then by the previous theorem, since its interior contains 0, so it is also balanced. So this completes the proof. So for any neighborhood, we can find a balanced neighborhood that is contained in it. For the convex neighborhood, we can find a convex balanced neighborhood that's contained in it. And if we apply this to a local base, corollary, so first, every topological vector space has a balanced base or balanced local base. In particular, if it is a locally convex topological vector space, by which it means that it has a local base which is member are all convex sets. So by the previous theorem, we have that this local base can actually be refined to a balanced convex base. So this will come in handy in later proofs. And finally, we prove some property regarding the local base. So this is theorem 1.15. That V be a neighborhood of 0 and first that Rm be a increasing sequence, strictly increasing sequence that goes up to infinity. Then X, the whole space, is covered by these neighborhoods, and from 1 to infinity. And the consequence of A is that every compact set is bounded. And C, if the neighborhood is actually bounded and given any sequence delta n that decrease to 0, then this collection forms a local base. So this gives us some convenient criterion about a local base and boundedness. So the proof, first part. So the first part is very easy. We just choose any arbitrary point in the space. We want to prove that we can contain this point for n large enough. So we do this by the fact that the multiplication, the scalar multiplication, is a homeomorphism. So we fix this x, and that's called this map. Just write like this. So it's from real number or the scalar field into the topological vector space. So we look at the image of this function. Oh, it's actually very confusing. Let's write it as v. Okay, so v, the image of v that is inside v, image of v inside v is open and contains 0. Then by the standard topology of real number or complex plane, we can find a ball be, say, epsilon of 0 in V, such that this neighborhood actually contains this ball. Then it follows immediately that for n large enough, this number will lies inside this ball. Actually, this is a real number, right? Because this sequence is real number. So let's just put it as real number. So one over Rnx is inside the neighborhood V. So actually, x is inside this neighborhood for every v, for every n, for every n onward. So this is part A. Essentially means that given any neighborhood of 0, you can just enlarge it infinitely, and you will eventually cover the whole space. And B is simply a consequence of part A, because so let's actually choose a balanced neighborhood. Balanced neighborhood contained in V. Then we do the same thing as in A. Contains in by A. Then by the compactness of, we didn't have a symbol. Let's call it K, a compact set. By compactness of K, there exists N1 up to Nm such that K is contained in Rn1W union up to Rnmw. Because W is balanced, these are all inside the largest one. So we can just simulate it like this. Let's write it as Rw for simplicity. Then this just implies that it's bounded, right? Because for any t larger than r, tw is containing rw as w is balanced, which implies that K is bounded. Part C, we have a positive sequence that decreases to 0, and V is now a neighborhood that is also bounded. Then the family delta NV forms a local base. So by definition of boundedness, that U be a neighborhood of 0, then there exists a positive number such that U lies inside V lies inside TU for T larger than S. Now, because delta N decreases to 0, exists a positive number, big N, which is a natural number, such that delta N times S is smaller than 1 for N larger than big N. Because this implies that 1 over delta N is larger than S, by the above condition, we have that V is contained in 1 over delta N U, which is the same as delta N contains in U for all N larger than N. So actually U contains O by finitely many of V. And this implies that delta NV is a local base, as the neighborhood U is arbitrary local base. And that's the end of the proof.